Good afternoon, Doctor. We are MAA111 Group 7, and today we'd like to present Markov chains. Before we start, I would like to introduce my team members. First of all, I am Ui Pei Yan, and my another two team members is Ling Peng Yu and Ahmad Adib bin Kamal. First of all, I'd like to introduce Markov chain. A Markov chain is a mathematical model that represents a system transitioning between different states based on probability. It was introduced by Andrew Markov in 1900 and is widely used in areas such as economy, genetics, machine learning, and search engine algorithms. One defining feature of Markov chains is their memoryless property. The probability of transitioning to the next stage depends only on the current state, not the sequence of the previous states. Linear algebra plays a significant role in describing and analyzing these transitions through the use of metrics and vectors. Next, we need to learn some basic concepts of Markov chains. First of all, states are the building blocks of Markov chains. They represent the different conditions a system can occupy. Understanding states allows us to define the system structure and analyze its behavior. Besides, we also have transition probability matrix. The transition probability are stored in a square matrix called the transition matrix, which is a central concept in linear algebra. If the system has n states, the transition matrix P is an n multiply n matrix where each entry Pij represents the probability of transitioning from state I to state j, which is the formula stated below. Each row of P sums to 1 because it represents a probability distribution. Now, you can write down the whole Markov chain as a matrix P like the below. Additionally, we also have the state vector. The state vector tracks the system probability at a given time. It's essential for modeling the system evolution. By using matrix multiplication, we can compute future state and determine how the system behaves over time. And also we have the evolution of the system shows how the state vector changes through repeated multiplication by the transition matrix. This provides a practical method for analyzing dynamic system and forecasting outcome, and this is called system evolution. We also have the stationary distribution. The stationary distribution reveals the long-term behavior of the system. It is particularly important for understanding systems that stabilize over time, such as ranking in search engine or equilibrium in population studies. Last but not least, we also have connection with eigenvalues and eigenvectors. The stationary distribution is linked to eigenvectors, and the transition matrix property depends on eigenvalue. These linear algebra concepts allow for deeper analysis of the system stability and convergence.
Hello and Assalamualaikum. My name is Ahmad Adib bin Kamal, and for my part, I will be talking about the relationship of Markov chains with linear algebra. The first thing that we'll be talking about the relationship between Markov chains and linear algebra is the transition matrix representation, in which that a Markov chain is represented by a transition matrix P, where each entry Pij denotes the probability of transitioning from state I to state J. The conditions for matrix P is that P is a square matrix and that each row must sums up to 1 as a probability distribution. For example, we can let P of matrix 0.8, 0.6, 0.2, and 0.4 be a transition matrix, and Wk be the state vector after k times. Then W1 we can get by multiplying P with W0, which W0 is equals to identity matrix of 1 and 0. Multiplying those two, we will get W1 of 0 0.8 and 0 0.2. Therefore, in order to obtain W2, we can multiply P matrix P with W1. Therefore, we will get 0.76 and 0.24. Uh, we can also denote the substitute W1 with P times W0. Therefore, we can also get W2 by multiplying with matrix P square times W0. So that it follows that in general, that Wk is equals to matrix P power to the power of k times W0. The next relationship that we'll be talking about is that the probability vectors and stochastic matrices. Okay, for the probability vectors, it has a non-negative components that sum up to 1. For example, W2 equals to a matrix of 0.76 and 0.24, which is a probability vector. For stochastic matrices, it is a square matrix whose columns are the combinations of probability vectors. For example, matrix P is 0.8, 0.6, 0.2, and 0.4, which is a stochastic matrix, in which that the stochastic matrix has that every column of the matrix is a probability vectors which would sum it up to 1. By combining the previous two relationships between Markov chains and linear algebra, we will relate them so that we will get the eigenvalues of stochastic matrices, in which that if P is a stochastic matrix, then 1 is an eigenvalue of P. This is that so that the columns of P sums to 1. Therefore, of rows of P transpose sums up to 1. For example, we can let X be the vector all of those components are equal to 1. Then we can denote that P transpose times X, which X is a columns of 1s. We can get back the X or 1X. This means that X is an eigenvector of matrix P transpose with the eigenvalue of 1. This means that P and P transpose have identical eigenvalues due to the same characteristic polynomial. Therefore, it follows that 1 is an eigenvalue of P.
Hello everyone, I'm Lin Pengyu. This is my part. This section is about the practical application of a Markov chain. First time, I need to introduce the page rank. It's one of the core algorithms of Google search engine, which uses Markov chain model to evaluate the importance of web pages. It analyzes the link relationships between web pages, constructs a state transition matrix, and uses matrix operations to calculate the ranking weight of each web page. Now, let me show the example to understand the page ranking in the practical application. Let's say the problem description, and we can see the figure there. The page link structure is page A links to page B and page C. Page B links to page C. Page C links to page A and page B. Based on the above structure, we can get the essential transition matrix. It's P equal 0, 0, 0 0.5, 0 0.5, 0, 0 0.5, 0 0.510. In the example, P and J is represent the probability of transitioning from page J to page I. And we need the incorporate random jump mechanism to it can address issue like downlink nodes and cycling structures. We incorporate a random jump mechanism. And there is a lot of parameters. We need to know this. The alpha equals 0.85 is the damping factor, and the n equals 3 is the total number of pages, and the others it is the random jump matrix. When we get the random jump matrix, then we will get the adjusted transition matrix. And then we need to use the iterative calculation to get the result. We can get the A, B, C, the probabilities. This animation is show the correlation process and display the change. It visualizes how the importance of web pages evolves over iterations. Each bar represents a page, and it high shows the likelihood of a user visiting that page. The page rank is widely used in search engines to rank web pages, ensuring that more important pages appear higher in search results.
Yeah, thank you for listening to our presentation, and we hope we clearly explained about the introduction and the basic concept of Markov chain, the relationship between Markov chain and linear algebra, and we also have the practical cases. So that's all for our presentation. Thank you.